Today we are going to learn about a new vocabulary word called momentum, and we define momentum as inertia in motion. So before we get into the specifics of momentum, we're going to take a little bit of time to review some old vocabulary that will be once again relevant in this chapter. The word momentum is defined as inertia in motion. So the first word we're going to review is the word inertia. We learned about inertia when we learned about forces and Newton's laws, and we said that inertia is the tendency of an object to continue its motion. When we talked about the word inertia, we elaborated that it means that it's going to maintain the same speed and move along a straight line path. So whatever direction it's headed, that is its direction. And we also talked about we also talked about the things that are going to affect the amount of inertia that an object has. And one of those things, and the most important thing to remember, is mass. It is dependent upon mass. What we mean by that is if we have two objects that are moving with some speed, let's say that we have a tennis ball and a bowling ball, and they are both rolling with a velocity of 2 meters per second. The more massive bowling ball is going to have a greater inertia, okay? So inertia is dependent upon mass. So when we say that we have momentum defined as inertia in motion, that means the more massive the object, the greater the momentum. Again, assuming that they are traveling, whatever objects we're comparing are traveling with equal velocities. When we say that our object is in motion, that means that our object must have some value for its velocity. So let's take a moment to review the vocabulary word velocity. This is defined as displacement divided by time. We also sometimes refer to it as speed with direction. Remember, we identified velocity as being a vector, which means that it can be illustrated with an arrow, and the values could be either positive or negative. And so we will be talking about the positive and negative aspect of this vocabulary word more as we get into our practice work and as we talk about conservation of momentum in a later lesson. But remember that velocity is a vector. And so if we say that momentum is going to be dependent upon an object's velocity, then that means that momentum is also going to be a vector. And so this positive negative velocity is going to correspond with a positive or negative momentum. We talked about the ability to change the velocity of an object. We said that the speed could increase or decrease, or that the direction our object is moving could change. And so that change in velocity is called acceleration. So acceleration is the change in velocity over time. And what that means is that we are taking the magnitude or the value for the change in velocity, and we are dividing it by the amount of time that it takes for that change to take place. So acceleration is change in velocity over time, or if we don't know how much the velocity changed, we might want to write this to be more specific, where we could plug in our final and initial velocities to represent that change in the numerator. So this is what we have learned in the past about acceleration. And remember that acceleration is not a natural thing. Naturally, objects have inertia, where they want to continue with the same speed and same direction. So objects naturally want to maintain a constant velocity. So if an object experiences an acceleration, there has to be something that created that acceleration. So we also learned about net force, which says that we have some sort of unbalanced force, and this force, or the sum of these forces to create that net force, this force is going to cause objects to accelerate. So if we have acceleration, it's because a net force acted upon our object in order to create that acceleration. Now we are reviewing all of these vocabulary words because they are going to be relevant to today's lesson. Momentum is going to be represented with a lowercase italicized p. And as I stated before, this is a vector quantity, so momentum is going to have a direction with it, and it will be able to be represented as both a positive or negative values in future calculations. Whatever direction our velocity is pointing, that's the same direction as our momentum. Our unit for momentum is going to be kilogram meters per second, and I'll explain that in more detail in just a second. And then in a later lesson, we are going to focus on something called conservation of momentum, which the main idea behind conservation of anything is that however much we have available is always accounted for. It may just move around as far as what contains that property or how much is represented in each individual piece of our big picture. So we'll talk about that more in a later lesson. It says here that momentum is directly proportional to both mass and speed. So here is our official equation for momentum. Again, lowercase italicized p for momentum, lowercase m is for mass. We're going to measure mass in kilograms. Lowercase v for velocity. We're going to measure velocity in meters per second. And since we are multiplying these two things together, our unit for momentum is just kilogram meters per second. Nothing simplifies, so it's all just expressed as our unit for the final answer. When we talk about relationships between our variables, remember that if we have mass and momentum set equal to each other and they are both in the numerator, then they are going to be directly related. What this means conceptually is if the velocity of my moving object does not change. Now let's say that we have two objects. So if the velocities of those two objects are the same, the object with the greater mass is going to have the greater momentum. Think about it, if I multiply it by a larger number, I get a larger answer. And because momentum is also equally placed according to the velocity, they're both in the numerator when I compare momentum to velocity, they are also directly related. If I have an object with a set mass, so again, let's take our tennis ball, whatever the mass of the tennis ball is, and I have the tennis ball move with 5 meters per second, I will get some amount of momentum. But if I take that velocity and I increase it, now instead of moving with 5 meters per second, let's say we make the tennis ball move with 15 meters per second, well, the increased velocity is going to result in an increased amount of momentum. So that's what we mean when we say that the mass and the velocity are directly proportional to momentum. Here I am asking a hypothetical question. Could a rollerblader, person on rollerblades, and a semi-trailer truck ever have the same momentum? The correct answer here is yes. Now, in order for them to have the same momentum, we must have our very small massed rollerblader moving with a large velocity, and at the same time, our very large mass semi-trailer truck must be moving with a small velocity. This is the situation that would allow them to have the same amount of momentum. Now, as we stated before, if the velocity changes, that is going to affect how much momentum my object has, because momentum is mass times velocity. So if I have an object that is moving with some velocity and it has a momentum, and then a little while later, that momentum has changed. It is not going to be the mass of the object that changed. It is going to be the velocity of that object that changed. So if an object experiences a change in its momentum, then it's because there was a change in the velocity. So a change in velocity over time, remember, is referred to as the vocabulary word acceleration. So acceleration is change in velocity over time. And so we have learned before that net force causes acceleration. So F equals ma is the relationship to allow me to comprehend how that force is actually going to affect the motion of my object which will ultimately be responsible for the change in momentum that it experiences. So this is saying that if a force is applied onto an object, the magnitude, remember that's just a word that means value, the magnitude of the force acting on the object is going to be responsible for determining the magnitude of the change in velocity. And because that is the variable that is going to determine the momentum for this individual object, then the force ultimately is going to affect the amount of change in momentum that the object experiences. Now, we have here change in momentum equals delta P. There are several different ways that we could calculate what a change in momentum looks like. So the phrase change in momentum could simply be expressed as delta meaning change, P for momentum. The way that I calculate the change in anything is always final minus initial. So I could say that if I wanted to calculate the change in momentum, I would simply say final momentum minus initial momentum. Now, if the problem does not tell me the value of the momentum before and after this change took place, then I could comprehend that there was a change in the momentum. Momentum is mass times velocity. Most people would be perfectly fine if I expressed a change in momentum as delta mv. But for today's conversation, I want to remind us that in these situations, at least for right now, in these situations, the mass of my object is not changing. It is a single object that has experienced a change in its momentum because the velocity changed. So I'm going to choose to take this expression and rewrite it so that I say mass times the change in velocity, because it's the velocity that's going to change. And just like we said before, change of anything is always final minus initial. So if you have a question that says that the velocity changed by a value of 15, then we would put 15 in the delta V. But a lot of our questions are not going to tell us that. They're going to tell us the speed of the object now, and then they're going to tell us the speed of the object later. So m times Vf minus Vi. These are all ways that we could interpret, express, write, calculate what the change in momentum is for our object. And this is just understanding how the vocabulary connects to each other. Now, the force applied onto the object is absolutely going to affect how much momentum change the object experiences, but it's not the only variable. The amount of time that this force is applied is also going to have an effect on that change in momentum. So if you think about somebody who is learning how to kick a soccer ball, how to hit a tennis ball, or anything like that, where we're kicking or swinging so that we're making contact with an object that is then going to send it in whatever direction we have just hit it, we often tell these athletes or these people kicking, throwing, hitting, whatever, to follow through with that swing or with that kick. And a lot of times students want to tell me that the follow through means that allows the person to hit the ball harder or kick the ball harder. It's not necessarily that they kicked or hit harder, but to say that it will most likely make the ball go farther, that would probably be a more accurate explanation or answer. To say that it's going to leave their bat, foot, racket, whatever club faster, that would also be an accurate answer. So when we ask people to follow through, it doesn't necessarily change the force. And in fact, in this case, I want us to address this as if you swing with the same force. One time you make contact and stop. The next time, using the same force, you make contact, but you follow through. What you have done is you have taken the force and you have simply applied it to the object for a greater amount of time. So because that force is being applied for more time, it's going to have a greater effect on our object, aka have a greater change in momentum, okay? So we now need to understand that it is both force and time together that's going to affect the change in our momentum. How much force and how much time is going to determine the magnitude of that change in momentum. In general, if we apply a force for a greater amount of time, then it's going to increase our momentum. Now, we have a new vocabulary word called impulse. Most of what you will see, impulse will be represented with a capital letter J. There are going to be a couple of questions or assignments where the author chose to write a capital I for impulse, but we're going to stick with a capital J here in the class, all right? So impulse, it says, is the product of force acting on an object and the time during which it acts. This is one of those definitions where we're basically giving you a math statement that's telling you to multiply force and time. So we have the equation here, impulse is equal to force times time. We are multiplying force in newtons times time in seconds. So we end up with impulse being measured in something called a newton second. It's just newtons times seconds. Now, if we are talking about relationships here, we need you to understand that force and time are inversely related. So real quickly here, it says, hey, you're about to crash. You're driving 60 miles per hour. Whatever you run into is going to bring you to a stop. So you're going to experience the same change in momentum, or I could say you're going to experience the same impulse regardless of what you run into. Would you rather crash into a brick wall or into a stack of hay bales? Well, most people would choose the stack of hay bales. Why? Well, a lot of times kids want to tell me because the hay is softer, which, okay, yes, but let's put it in terms of our vocabulary. When you come to a stop in the brick wall, that is instantaneous. It takes a very small amount of time to bring you to a stop. Therefore, the amount of force that is needed to stop you has to be a huge force. It's a big force to bring you to a stop so quickly because you're driving 60 miles per hour. If we crash into a haystack, we are now going to take a little bit more time for us to come to a stop. And don't get me wrong, it's still going to be quite the force that's going to be needed in order to bring your car to a stop because you're going 60 miles per hour. But because we have more time to stop us, the force that is needed to bring us to a stop is now less than it was when we hit the brick wall. So force and time are inversely related. More time to stop means a lesser force needed to create that change in momentum. Less time to stop means a greater force is needed for that impulse. So make sure you understand the relationship between these two and this concept. You will be asked questions in the future. So if I asked you, could you tell me why are airbags helpful? Why should you wear a seatbelt? And it's going to be questions like this pertaining to that relationship between force and time. Okay, so the force is applied for some amount of time, which is going to cause what we call an impulse. It creates an impulse, which is going to cause the momentum to change, the amount of momentum the object has to change. So the last thing that we are going to look at today is something called impulse momentum theorem, and it's just putting the two pieces together. Impulse is going to cause that change in momentum. So it says here in words, impulse is equal to change in momentum. So impulse we will express with a capital J is equal to change delta momentum P. So let's just back up to this list we made earlier of all the different ways that we can represent a change in momentum. Change in momentum delta P could be PF minus PI. It could be M times delta V. Or if I don't know delta V, it could be M times VF minus VI. We can now also add F times T. Force times time is equivalent to the value of the change in momentum the object experiences. J is our symbol for impulse, and that is equivalent to the value of change in momentum that the object experiences. Please make a list like this and put it somewhere for you to reference when you are doing your practice work. You are not going to be provided this series of expressions in the future. You will need to take whatever information that you are given in the problem And you're going to use that information to plug in whichever version of change in momentum you need in order to perform your calculation. So please understand that all of these things are interchangeable. They are synonymous. They are equivalent to each other. So I can use any version of change in momentum that you see here for any of the questions. It just depends on what am I given in the problem and what variable am I solving for, okay? So I will give you one additional equation, and it is basically relating these two together. Our delta P is going to be the same as mass times the change in velocity. That goes back to the main idea that we started, that momentum is mass times velocity. If the momentum changes, it's because the velocity changed. J, which stands for impulse, is the force applied to our object over some amount of time. If I multiply force times time, that tells me how much the momentum changed. If I can multiply mass times the change in velocity, that is telling me what the impulse was that was put onto that object, okay? So this is the information that we need you to understand about momentum. Remember, momentum is a vector. So as you work through the problems, pay attention. If they give you direction or if the direction has changed, you'll want to make sure that you make those positive and negative adjustments along the way.